Hello everyone, and welcome to the AI Research Roundup. I'm your host Alex, and here we dive into the latest in AI research. Today, we're looking at a survey paper titled Efficient Reasoning Models, a Survey. Basically, reasoning models have gotten really good at complex tasks using techniques like chain of thought. But this sort of slow thinking approach, generating lots of text step by step, uses up a lot of computation. So this survey provides an overview of how researchers are trying to make these reasoning processes more efficient, specifically by making the reasoning chains shorter, the models themselves smaller, or the whole inference process faster. So this first figure, figure 1, it basically gives a nice visual overview of those three main strategies we just mentioned. You can see them laid out clearly, shorter, smaller, and faster. The shorter section visually represents ways to make the chain of thought shorter, showing icons for things like reinforcement learning, supervised fine-tuning, prompt-driven techniques, and latent reasoning. Then the smaller row illustrates how to build compact models, pointing to distillation, quantization, and pruning, and combining smaller models with reinforcement learning. And finally, the faster section shows methods for speeding up decoding, like efficient sampling strategies and problem decomposition. It's a good map of the different approaches. Figure 1 showed the strategies, shorter, smaller, faster. Figure 3 here really drives home why those are needed. It points out issues like overthinking, where models generate ridiculously long reasoning chains for simple stuff. You can see the example asking what 1 plus 2 is. It also shows that longer isn't always better for accuracy. Sometimes performance actually drops off if the reasoning gets too long, which is that when more is less graph. And, well, lengthy reasoning costs more computationally, and can even introduce safety risks, so efficiency helps with resources and costs too. So we saw why we need efficiency. Figure 3 showed the problems with long reasoning. Now, Table 1 here digs into that first strategy we mentioned, making the chain of thought shorter. It lists a whole bunch of specific methods, things like using reinforcement learning, or special prompting techniques, and even latent reasoning where the thinking happens internally without spitting out all the steps. The table compares them by looking at the speedup they achieve, measured either by reduced latency, shown as L, or fewer tokens, shown as T. You can see some pretty significant gains, like, break the chain, achieving over 4x token reduction, and latent methods, like coconut, getting up to 5x faster latency. So these techniques really work to cut down the reasoning length. So Table 1 showed ways to make the reasoning chain shorter. Now, Table 2 here shifts focus to that second big strategy, making the models themselves smaller while keeping them good at reasoning. This table summarizes methods like distillation, where you teach a smaller model using a bigger one, and also reinforcement learning. It lists different techniques, the kind of data they use for training, like COT data or mixed data, and importantly, the accuracy improvements they get on benchmarks like GSM-8K and AIM. For example, DL-COT, using distillation, achieved over 93% accuracy on GSM-8K with an 8 billion parameter model. And down at the bottom, DeepSackler used reinforcement learning to get over 43% on the tough AIM benchmark with just a 1.5 billion parameter model. So you really can build smaller, more efficient models that still reason effectively. So we've talked about making reasoning chains shorter with Table 1 and making the models themselves smaller with Table 2. This brings us to the third main strategy, making the decoding process faster. Table 3 here dives into exactly that. It lists methods grouped into types like efficient self-consistency and efficient sampling. These are techniques designed to speed up inference, like when the model generates multiple possible answers and picks the best one. The table shows the change in accuracy on GSM-8K, which is often pretty small, sometimes even a slight increase, and then this efficiency up ratio. This ratio measures speed up in different ways, like reducing the sampling count, shown as S, reducing latency L, or cutting down computational cost C. You can see some really big numbers here, like fast best of n, achieving almost a 40x speedup in latency, and methods like DSC reduce the cost by up to 5 times. So these techniques really tackle the speed of getting the final answer out. So we've looked at tables focusing on each strategy individually, shorter, smaller, and faster. Table 5 here kind of brings it together by showing how different methods from all those categories perform on a really challenging math benchmark called AIME. It compares accuracy and, for some, the number of tokens used against an original large model baseline which gets about 70% accuracy using over 10,000 tokens. You can see methods like DAST, which is shorter, getting 53% accuracy with significantly fewer tokens. In DeepScala R, a smaller model achieves 43% accuracy using just a 1.5 billion parameter model. So it really highlights the trade-offs on these difficult tasks. You often gain efficiency, but might sacrifice some top-end accuracy compared to the biggest models. So looking at all this work together, it's clear there isn't just one single path to making these complex reasoning models more efficient. The key takeaway really is this multi-pronged approach, making the reasoning chains shorter, the models themselves smaller, or the generation process faster. This kind of research is really vital because it helps bring powerful AI reasoning capabilities out of the lab and into practical applications where speed and cost actually matter. Well, that's all for today's AI Research Roundup. Thanks for tuning in. I'm your host, Alex.